Good evening, everyone. I'm Preetha from Techno College of Engineering, Agartala, welcoming you all in the eighth technical session of third international workshop on advanced seismology, seismic hazard, and earthquake engineering, ASSHEE 2021. Now I request Professor Antonella Peresan deliver her lecture on time-dependent earthquake and tsunami hazard, a scenario-based approach. Dr. Antonella Peresan is a renowned seismologist working in National Institute of Oceanography and Applied Geophysics, OSG, Italy. Her research interests are earthquake predictions, neo-deterministic method, seismotectonics, geophysics. She has more than 1,500 citations in research arena. Now I request ma'am to deliver her lecture, and I also request J.R. Khalsar for chairing the session. Now I request ma'am to deliver her lecture. Ma'am, please.
Thank you so much for your kind introduction. I will try to share my screen with the slides right now. Is it okay?
Yes, ma'am, it is visible.
Perfect. It's a full screen, I hope.
Yes, ma'am.
So, first of all, I would like to thank the organizers for inviting me and providing this opportunity to share the results of our research. During this talk, I will try to provide an overview of the results and the recent advances in time-dependent earthquake and tsunami hazard assessments, which are based on neo-deterministic scenario-based approach. And well, I would like to recall that the results I'm going to present are the result from a long-term fruitful collaboration with scientists from many countries worldwide, including Russia, Egypt, and of course, India. Well, I will just try to go through different aspects of our research, and I will be pleased to provide the materials if anyone is interested to deepen any of the presented research. So why to use a scenario-based approach when dealing with seismic and tsunami hazard assessment? Well, the first reason is that we may need different earthquake and tsunami hazard maps for different purposes. So for different scopes, we may need a different description of the hazard. For instance, long-term hazard estimates can be suitable for territorial planning or for insurance purposes, whereas the time-dependent scenarios at the intermediate-term scale may be more useful for emergency management. And detailed local scale scenarios with no dependence in time may be suitable for engineering design of critical infrastructures. Moreover, the limited data availability and the related uncertainties impose some limitations in the statistical description of seismic and tsunami hazard based only on empirical characterization and statistical characterization. And in this framework, parametric tests and also modeling of physics-based scenarios, considering a wide set of possible sources, may contribute to fill in the gap in available observations. So, forecasting earthquakes and the related ground shaking, we know it's really a difficult task because of the huge uncertainties involved, the limited data sets, the heterogeneity of the available information, which in some, let's say, in an avoidable sense, they will reflect in the uncertainty in the obtained results. Anyway, any reliable anticipatory information that we can get, even uncertain one, can be effective, can be appreciated by the population for possible actions, and also as a reminder and warning of looming disasters. And also it should be considered as complementary to design and construction of seismo-resistant infrastructures, but not replacing them, of course. Anyway, the operational earthquake forecasting, as well as the tsunami hazard assessment, the earthquake hazard assessment, to be fruitful, to be used, must be reliable. They should have a confidence. They should be tested and confirmed by evidence, and they do not need to be necessarily probabilistic ones. What I would like to stress once more is that only by checking carefully the methods we are applying against the observation from future and then independent events, only by carefully recording the failures and successes in describing what is happening in the future, may allow us to evaluate in a rigorous way the reliability and effectiveness of the methods forecasting or hazard assessment. And this is also necessary for communication to decision makers who are, we need the information about the confidence and the uncertainties related with our estimates. So what about earthquake forecasting? We heard on the very first day the lecture by Jim Murray, who was providing many examples of different kinds of forecastings based on different observables. And he was pointing to the, let's say, limitations and successes that are quite limited by the different prediction methods that were applied. Anyway, since the 80s, it is well recognized that the lithosphere of the Earth behaves as a complex and nonlinear dissipative system. And these kind of systems are predictable to some extent, but only up to a limit and after some substantial averaging. So they are not predictable exactly with very high precision, but on average and with some limits, some uncertainties. According to this view, the view of complex systems, the forecasting problem can be posed as a step-by-step multi-scale process where we narrow down the space and time and magnitude range where the earthquake is likely to occur. However, reducing the uncertainty in the forecast of an impending earthquake is not for free, so it requires using at each step additional reliable and tested information. So we cannot expect from the same data to squeeze more and more information and to come to a very precise forecasting, but we need at each step some additional information that may better constrain the prediction, the forecasting. So since decades, the experts in earthquake forecasting are making use of the clustering in earthquake sequences that are observed at different space-time scales. So the precursors, possible precursors that are observed in seismicity are one of the most widely used feature for issuing forecasts. The reason is that for seismicity, we have quite a broad, quite a huge amount of information, which is provided by Earthquake Catalog in a systematic way, and also on a quite long time span, which eventually allows to design the algorithms and methods for forecasting and to test them. Whereas for other observations, only recently, we have the possibility to collect in a systematic and let's say in a broad area the necessary observables. And this is the case of deformation that was also mentioned by Jim Murray and that was proposed many years ago, but then remained untested because of the lack of information, basically. For instance, among the algorithms that have been proposed for earthquake forecasting based on seismicity patterns, the algorithms CN and the MATE allow, that we are going to consider in this presentation, allow to diagnose in real time, so in a prospective mode, the periods of time when the probability for the occurrence of an earthquake with magnitude above a given threshold is likely to occur. And these forecasts are done at the intermediate term middle range scale, which means with the time uncertainty of months to years, and within areas of alarm of the order of 100 kilometers. By integrating information from different observables, which can be geochemical or electromagnetic or the deformation pattern or GPS information, as we are going to see, may allow to better constrain the forecast. So starting from intermediate term scale, that as we will see, it's quite feasible, viable possibility. We may try to reduce the uncertainties by incorporating additional information, but we have to be aware that this information must be also systematic, tested, and properly checked for the uncertainties. So let's see how these methods are working in practice when we apply them for real-time prospective testing of earthquake forecasting in Italy. Well, in Italy is one of the few countries where the two algorithms, CN and DMAIT. CN comes from California, Nevada region where it was first designed, and DMAIT comes from magnitude 8 events. That was the first set of events of earthquakes for which the method was designed originally. So these two algorithms that were proposed now about 3 decades ago are applied on a routine basis to perform intermediate term middle range forecasts. DMAIT and CN are based both on a set of empirical function of time that allow us for a quantitative description of the premonitory seismicity patterns which may occur within a predefined territory. And these patterns include the variations in seismic activity, the seismic quiescence, and also the clustering in space and time of the events. The main features of these algorithms are that they are fully formalized, the codes are available for independent testing, and they make use of routine data which we can find in earthquake catalogs, for instance, USGS earthquake catalog or ASSHEE 1. And they are undergoing prospective testing since about 30 years on a global scale. In Italy, we started a real-time earthquake prediction experiment in July 2003, so now it's about 2 decades. And the forecast by CN and DMAIT algorithm are regularly updated, CN every 2 months, DMAIT by every 6 months, and they are posted at these links where you can find the full archive of predictions, whereas the current predictions are protected by password, but the password can be requested by, let's say, guaranteeing that the information will not be disclosed. And the experiment in this way allows to check in real time whether the forecasts are really correct or wrong ones, and so to assess the significance of the provided result. For the application of a DMAIT algorithm in Italy, we consider a spatially stabilized variant of the algorithm where the seismicity is investigated considering a dense set of overlapping circles whose radius is proportional to the magnitude of the target events. In Italy, we are performing the forecast by DMAIT considering 3 different magnitude ranges, from 5.5 to 6, from 6 to 6.5, and from 6.5 to 7. Here you can see the list of events which occurred since the algorithm is applied in prospective mode. So, and here you can see some examples of events. The alerted areas are in yellow, and you see the dots, the red dots are events forecasted by DMAIT, the blue dots are the failures to predict. For the application of CN algorithm to the Italian territory instead, it is necessary to define a priori the area of investigation. So there is no automatic way to select the territory. In Italy, we are currently testing a regionalization for CN application, which is based on the seismotectonic information. So the 4 regions which we are currently monitoring since more than 2 decades now, that you can see in these 4 maps, have been defined, taking into account the tectonic setting, geodynamic information, and in particular the seismotectonic model for the Italian peninsula and surrounding regions that were defined independently by different researchers. Basically, the northern region is composed by compressional, contractional zones which border the northwestern boundary of the Adriatic microplate, whereas the central region is composed prevalently by extensional zones that mark the subduction zone, the subduction of the other plate beneath the Apennines. Whereas the other region, here in blue, corresponds to the foreland areas that compose the Adriatic microplate. Well, here in this table, you can see the earthquakes which occurred since the CN algorithm is applied in prospective mode to the Italian territory. And you can see that out of 13 earthquakes that occurred so far, 11 were correctly forecasted by CN algorithm, with 2 failures to predict in blue, and the other events all preceded by an alert in the corresponding region. In this table, the results by a mate algorithm application to the Italian territory are summarized, both considering retrospective time span and for prediction results. And we can see that, for instance, if we consider the events, the earthquakes, target earthquakes in the magnitude range from 5.5 to 6, we had 6 events out of 11 correctly forecasted by a mate with the space-time volume of alarm, which means the total time and space occupied by alerts, around 24%. And well, the confidence level of such predictions, if we consider all the time span from including both retrospective and real-time prediction, is above 99%. But also, if we consider only the forward prediction, the confidence level is around 93% so far. This is a similar table defined for CN application to the Italian territory. Again, we have divided the different time intervals, including retrospective, investigation, and forward predictions. And we can see that by CN algorithm, 11 out of 13 earthquakes were correctly forecasted, with a space-time volume of alarm around 33%. The confidence level of such predictions is above 99%, which means that the probability of getting similar results by random guess, so for instance, declaring alarm by just tossing a coin, is below 1%. So this confirms the high confidence level of the results obtained so far. The quality of forecasts can be also characterized by, in a graphical way, by considering the error diagram or Molchan diagram, where the rate of failures to predict is plotted versus the space-time volume of alarms. All the points that lie on this diagonal line, correspond to the results of a random guess. So those which you could receive just declaring randomly the alarms. And the closer we are to the origin of the axis, the better are the results. And we can see that the results obtained by CN algorithm are sitting here. So either in prospective and forward, let's say, overall predictions. So all of them fall in an area of high significance below the 95 percentage confidence level curve and also below the 99 confidence level curve. Also, the results of a mate algorithm are in an area which is different from results of a random guess, but the algorithm CN still outscores the mate algorithm. This might be explained by the fact that by the contribution of the seismotectonic information, which seems to provide valuable indications to improve the results of forecasting algorithms. The significance of the CN and the mate algorithm performances has been independently assessed and confirmed also in the report of the International Commission on Earthquake Forecasting that was established after the L'Aquila earthquake in 2009. And well, this study confirms basically on a global scale the results we obtained for Italy, confirming that these predictions show a skill that is statistically significant. What is important is that these results have been obtained in a real-time prospective mode. So actually, these are real tests on independent data, which supports the feasibility of earthquake forecasting, at least at the intermediate term space-time scale. The method used for assessing, for evaluating prediction results, it's important, and this, I believe, as I was trying to stress also during after the lecture of Jim Mori, so we should put more effort in systematic testing of methods for forecasting, any methods, either based on precursors or statistical one. And it's very important to define properly the scheme for significance, for evaluation of the prediction results. Because many times we can see either the main bias, the most, let's say, frequent bias is in the cherry picking of good results and, let's say, overlooking of inadequate results, or in many other instances, the statistical tests are applied within a sufficient sample size. For instance, when you have only one event, only one target event, and this is a situation which is non-statistical, and therefore the significance cannot be assessed in this case. But also there are more subtle problems in evaluation of the forecasting results, and also in the evaluation of, let's say, seismic hazard assessment results that may be more, let's say, subtle, more difficult to identify. For instance, the parametric gambling score that was designed for probabilistic forecasting has been applied also for alarm-based predictions, but as demonstrated by Molchan in 2017, this adjustment to alarm-based tools was made in such a way that the results, the outcomes of the testing are independent from the prediction results. So independently on how many earthquakes you forecast or the time span you are considering, then the results, the outcome of the test just depends on the time of the, let's say, duration of the time span which is used for the forecast. So it is independent from the prediction result, which is obviously not a good method for testing. So I just would like to stress the need to work much more on these aspects of testing the prediction, the forecast, and in general of the results of our research. So let's see how we can proceed. We can make a step ahead in this forecasting. So we have seen that the earthquakes, by their, let's say, complex nature, cannot be predicted with ultimate precision, but still we have seen that some algorithms exist that allow, in a, let's say, significant way, to perform intermediate term middle range forecast. And CN and the MATE are just two examples. So the alerts may be issued that refers to quite broad areas with the dimensions of 100 kilometers and with a duration of several months to years. So such uncertainties are obviously not compatible with any evacuation or a red alert. Still, we may imagine many different ways to use this information to improve, let's say, to implement many prevention actions, ranging from planning to, let's say, awareness raising, let's say, trainings. So the main question is, can we try to use additional independent information to reduce this uncertainty either in space and or in time? So a first attempt to reduce uncertainty based on satellite information, namely GNSS anomalies detected by ground positioning systems, satellite Earth observation, was performed, for instance, in the framework of the SISMA project funded by the Italian Space Agency, where the anomalies of in deformation were computed considering a configuration of the available station, GNSS station available so far. This configuration of polygons was defined, and within each polygon, it was possible to identify, let's say, a state of anomalous deformation. This deformation, these anomalies, were combined with information provided by seismic anomalies, for instance, the areas alerted by CN, to produce this kind of, let's say, combined maps of alerted areas. However, as you can see, in many areas, the uncertainties were pretty large, and the results were not so very obvious, especially in the integration of the many, let's say, different states of alert from GNSS and CN. So more recently, we tried to explore the synergic use of GPS and seismological information in a different way. So following a new approach, where the seismotectonic information and the seismicity patterns are used as a kind of prior information to guide the analysis of geodetic data. So in this case, the velocity and strength pattern is no longer assessed on a two-dimensional, let's say, plane, but rather the deformations are investigated along one-dimensional transects, which are properly oriented with respect to the tectonic setting of the region, and specifically with respect to the regions monitored by CN. To explore this new approach, we carried out two exercises, two experiments. One focused on the Emilia earthquake, which occurred in 2012, and the other one focused in the area of the Amatrice earthquake sequence, which occurred in 2016, by performing a retrospective analysis of GPS and where available also SAR data. So as I mentioned, the GPS observations are used to estimate not the two-dimensional to the velocity field, but rather the velocity and strain pattern along one-dimensional transect. The transect width is defined trying to, let's say, combine, to follow two criteria. One is to make the region, the transect, as narrow as possible, but at the same time, we need to include let's say, as much as possible number of GPS stations in the area. And one of the important criteria is to consider these transects in area of homogeneous tectonic features. So initially, we considered 6 transects with about 50 kilometers wide, so plus minus 25 kilometers from the line. consistent with the zonation by CN algorithm. So in red here is the central Italy region monitored by CN. And you see the 3 transects. These are the set of stations. And here it's another set of 3 transects in the area of the Emilia earthquake. So the time span of available observations for these areas is around, let's say, starts in 2005. So for the Emilia earthquake, we had, before the event, 7 years of observation. For the Amatrice earthquake, we had something like 11 years of GPS data. So our question was whether these, these information were let's say, allowing us to perform to reduce the uncertainty in CN forecasts. So let's see which are the results which we obtain. So first of all, analyzing the time series along the transects, and especially those around the, let's say, this transect crossing the epicenter of the earthquake which occurred in Amatrice in 2016, this data evidenced some stability over time. So they did not really change in time in the available time span of 11 years. So the variations were quite stable. But and this was assessed considering 14 GPS stations that were active for most of the time, so at least 2/3 of the overall time span. So no significant time change was detected there. And the most significant aspects are related with the space changes in the GPS deformation. So if we consider this is the distance along the transect, here distance 0 means passing through the epicenter of the earthquake. If we consider the velocities along these 3 transects, we see that in Camerino transect, north of the epicenter, we see just a velocity which is increasing from west to east, which is compatible with the extensional domain for this area. Similar trend we can observe in the Raiano transect here, from west to east. Again, we can observe an extensional trend, which is compatible with the velocity increase from one side to the other of the transect. And here we have the Adriatic plate in this area. However, when we consider the transect passing through the epicenter of the earthquake, we see that we have a stable situation here with no significant velocity, so the velocity is constant. But we have in this area about plus minus 25 kilometers, 30 kilometers from the epicenter in both sides. We have a significant anomaly in a very fast deformation, which is not compatible with this long-term tectonic trend, which is observed north and south of Amatrice. As a counterexample, we also consider an along strike transect. So the extension is along this direction. This is just located parallel to the maximum extensional trend of the Apennines, and we see that no geodetic signature could be observed along this direction. Well, let's move to the Emilia, the area of the Emilia earthquake. Here the situation is a bit more complicated. We are in a compressional domain, which is characterizing the northern border of the Adriatic plate, the boundary of the Adriatic plate, north of the Apennines. And here we consider again, so this is the maximum compression direction. We consider first 3 transects across the strike, so in this direction, and then 3 additional transects along the strike, like we did for Central Italy. Here the situation is a bit different. What we observed a cross strike, so in the direction of maximum compression, is just the compressional, the tectonic compression that characterizes the area. So a velocity decreasing from here to there. So this is the direction of compression. And actually what we see with the cross strike transect is just this decreasing velocity. But if we investigate the deformation in the along strike transects, we see that for this one, which is the most distant from the epicenters, we do not see any, let's say, it's a quite constant one. But the most interesting features are here along these and these transects. We see that the epicenter of the earthquake is here, so distance 0 from the, let's say, epicenter. So this is the location along the transect, sorry, along the transect here. And we see that at one side and the other of the earthquake, of the epicenter, we have opposite directions of the velocity. So here it's increasing, here it is decreasing. So this pattern is compatible with the strike slip mechanism rather than a compressional one. And actually, if we consider the results from impart inversion of the seismic sources for these earthquakes, we can see that in this area, the events have a significant strike slip component, which is compatible with this observed trend. So these results suggest that the GPS data analysis along transects is able to capture the deformation which is occurring before the earthquake, because in all these diagrams, which I've been showing you, only the data up to the earthquake have been considered. So no co-seismic effect is involved in these plots. So these results are quite encouraging, but as I mentioned, these results, any results, need to be systematically investigated and tested. And work is in progress to systematically check over the Italian territory the combination between seismological and geodetic signatures, considering a wide set of transects, which you can see plotted here, along with the epicenters of the largest events which occurred in the area, and that are properly oriented according to the CN regions and the tectonic setting of the investigated territory. So based on these results, we will be able to see whether these actually can contribute in a statistically significant way to improve the forecasts. So just to summarize, we have seen that the one-dimensional analysis of geodetic data along these properly oriented transects shows that the GPS data may highlight the geodetic signatures which are stable over time, so do not provide really temporal information, but rather they permit to focus the area of strain accumulation within the regions which are alarmed by based on, let's say, seismic anomalies. So the geodetic signatures are a long-term phenomenon, but still their integration with information, space and time information provided by CN, for instance, by other prediction algorithms, may significantly reduce the space uncertainty of alerted areas. And so we can move from intermediate term middle range forecast to narrow range forecast. So at least one of the components can be, let's say, restrained. Also, we have other information that can be combined with the information provided by prediction algorithm. And in this scheme, I just show that what we have been discussing so far, we can combine the information from formally defined algorithms for intermediate term middle range forecast with information that's provided by geodesy can assess star. And this information may provide intermediate-term narrow-range forecasts, which again can be combined with further information provided by the modeling of ground shaking by the neo-deterministic approach. And in this way, we can derive some space and time information for seismic risk mitigation, as well as the input for engineering analysis, which is provided by, as we will see, the modeling of synthetic seismograms by the neo-deterministic approach. So just to briefly introduce the neo-deterministic approach to seismic hazard assessment, well, the method allows to define the hazard from the envelope of the values of ground motion parameters, which include acceleration, velocity, or displacement, which are defined by modeling not a single scenario earthquake, but a wide set of possible sources, which may include also the maximum credible earthquake or any information that support the occurrence of an earthquake with a given magnitude in the area. This approach allows to incorporate any new available information provided by geology or geophysics, any sound information, including information about the occurrence rate when available, and the space and time information about the impending earthquakes, which may be provided by forecasting methods. Also, this method, this approach allows to account for the uncertainties and the gaps in available observations by considering a wide set of possible scenarios, even not yet observed, and by performing parametric tests over the, let's say, given uncertainty. This scheme provides, this flowchart describes how the method works. Basically, the information about structural models in the area and about seismic sources as described by focal mechanisms, seismogenic zones, and earthquake catalogs available for the area. All these informations are used to define the potential seismic sources that are distributed over a regular grid which cover the territory. And then all these sources are modeled by considering the wave propagation in along these structural models, and the time series, complete time series. So the synthetic seismograms are computed at the nodes, at the receivers, which are placed at the nodes of a regular grid again. And from this wide set of synthetic seismograms, which remain associated in this way to each node, it is possible to extract the peak ground values, the maximum values of shaking, for instance, from the different possible sources. And in this way, it is possible to draw maps like this, where velocity is represented, but also acceleration or displacement can be obtained as well, because at each node you have the complete synthetic seismograms. In this stage, in this step of the modeling, it is possible to account for the information provided by alerted areas, restraining the potential sources within the alert territory. And in this way, it is possible to obtain scenarios of this kind where the ground shaking is associated only to the sources within alarm territories. This is, for instance, the scenario of velocities associated with the northern region, central region, you see, which is displayed in dark gray. And here we have mapped only the velocities which exceed 15 centimeters per second. So the areas where actually we expect a significant damage associated with potential earthquakes within this region. So far I explained how these methods work, but well, do they really work properly? So let's see how they perform in occasion of the most recent strong earthquakes in the area. Specifically, we consider the 2016 Central Italy earthquakes, magnitude 6.2 and on August 2016, and magnitude 6.6 in October 2016. So both the events were predicted correctly by CN algorithm. It's important to stress that the alarm that was lasting from 1st of July till 1st of September was confirmed by the first event in middle August, the Amatrice earthquake. Then, when updated on September 1st, the algorithm was confirming again the alert, and in October 30, we had a second, we had a second strong event, magnitude 6.6 in the area of Norcia. So these were both successfully predicted. On the other side, the algorithm made, you see the epicenter, this was the situation of alert when the earthquake occurred in Amatrice, and it was missed because it was just in between two alarm areas. Interesting to see that just let's say 6 months in advance, the area was in state of alarm, but the alarm was closed, was shifted north and south, and so it scores formally as a failure to predict by a mate algorithm. So you see, this was the situation 6 months in advance, but then the situation changed, and it was not predicted by a mate. Well, let's consider, so the Amatrice and Norcia earthquake were both forecasted by CN. Let's consider the ground shaking, which was associated to that area. Well, in this area, a shaking between 0.3 and 0.6 G was expected according to the neo-deterministic approach for the sources within the yellow area. And actually, the earthquake confirmed these values with a 0.45 G acceleration for the Amatrice and 0.6 G for the Norcia earthquake. These, let's say, the uncertainty of forecast could have been potentially reduced by considering the GPS information, by taking into account the transect where geodetic anomalies were observed. If we would have had that information, we could focus our attention on this area at the intersection of the transect with geodetic anomalies and the alarm area by CN. So it could have been worked properly, but that was retrospective. More important is that also some more detailed analysis can be performed, not in terms of forecasting, but in terms of modeling the ground shaking. So after the Amatrice earthquake in August 2016, we realized that in that area, even a larger magnitude event could occur because they were observed in the past. So we performed a large number of modelings for different configuration of sources in the area just after August, and these are the results that were obtained in advance of the Norcia earthquake, so before the occurrence of the Norcia earthquake in October 2016. And you can see the gray area is the envelope of the ground shaking model by the neo-deterministic approach, and this gray line, continuous line, is the recorded ground shaking in terms of spectral acceleration for this event. So you see that the observations for the Norcia earthquake were fitting very well the predicted ground shaking model by a neo-deterministic approach. And it's very interesting because, especially in this part of the spectra, we have let's say, non-trivial behavior, which could not be captured by the standard shape of the, let's say, the spectra predicted, let's say, given associated by the regulation in Italy. So this shows that the method is really was really able in this case to capture this complexity, this feature that was not captured by the two simplistic models that were given by the regulation. The advantage of this neo-deterministic approach is that it provides the spectra, as you have seen, but also complete synthetic seismograms that can be used, and is of interest, of course, for the engineers, to model the dynamic behavior of the structures. And this is a study we carried out for a historical building in Trieste, where let's say, the complete time series was given as input to a commercial software for modeling the behavior of the building and to see which were the areas that could be subject to damage in case of a large magnitude 6.5 earthquake nearby Trieste, which was not yet observed so far. So we can imagine even some scenarios that are potential but not yet observed. Also, it allows a method to investigate more, let's say, specific features, such as the differential motions between pillars along a bridge, and other similar features that can be relevant for the monitoring, for the, let's say, design of critical infrastructures. I would like to point to the fact that these models are not just for academic purpose, but an application has been developed which is accessible online, which can be used online, so as a user-friendly interface, and allows to, let's say, to apply neo-deterministic approach for the modeling of ground shaking, either at national scale or at local scale. Well, I still have some time to, I hope, to shift from land to the sea. So everything I was showing so far was related to earthquakes which occurred in land, but what if the earthquakes are having epicenter in the sea, as it is the case of the two most recent target events which occurred in the Adriatic Sea region in 2019 and this year, let's say in March this year, respectively. So for these two events, we see they were both forecasted by CN algorithm within the Adriatic region. So there was an alert for this quite wide territory, which has a low seismicity territory anyway. Both events were forecasted by the algorithm. Also, the MATE algorithm was able to forecast the event occurring here in the middle part of the Adriatic this year, whereas the other event was outside the monitored territory. The neo-deterministic modeling can also be applied in a simplified, let's say, version to model tsunamis. And let's say, an early application that was carried out some years ago by Paolato and other colleagues, considering different possible sources in the Adriatic Sea, also a source in the Dures area where the earthquake in 2019 occurred was considered. And that study, that modeling, was showing that events occurring here with magnitude 7.0 or larger may generate some significant tsunamis, whereas events with magnitude 6.5 or lower do not provide any, let's say, significant tsunami, maybe just nearby the source, but still very limited effects. So, according to this study, those two events should not generate any tsunami alert. And in fact, this was confirmed by, this was confirmed by the recently settled system CAT-INGD, the tsunami alert system that was set up for the Mediterranean. And for these two earthquakes, we had an advisory message that was issued for the Dures earthquake in November 2019, and which was magnitude 6. And the alert was called back 3 hours later, but we knew in advance that from the modeling that no significant earthquake should be expected. And for the magnitude 5.5, no, just an information message was issued. So again, the modeling was correct in providing the information in advance of the earthquakes. But we cannot exclude, as it was for the Norcia earthquake, the possibility for larger events, and using available information about bathymetry and topography that we have for the Adriatic Sea at different scales, and using information about tsunamigenic sources in the area, we can figure out some scenario sources with magnitude as large as 7 or 7.5. This is an exaggerated, let's say, bathymetry for the Adriatic Sea. You can see it's very shallow in the northern part, which is a good news for the tsunamis. And we apply the NamiDense software. We use this modeling software, which is basically a software based on the solution of nonlinear form of the long wave equations. And using this code, we modeled, for instance, these different segments of the source, which was activated by the 5.5 event in March this year. And we could see this is the maximum amplitude associated with the with this scenario source, and these are the simulated mareograms along the Italian coast. This is a different configuration of, again, on the same active fault, but different segment. And you can see that the scenario is much different. So by combining all these scenarios, we may have a different picture of things which, I mean, the situations that may be observed with the reactivation of sources in the area. And currently we are working in the northern part of the Adriatic coast in this area. And what we can say is that thanks to the shallow bathymetry for this area, all the events which may occur in the southern part of the Adriatic reach this, the possible waves reach this area only after significant time, which is good for any action, mitigation action that we can take. And this is an example of the inundation map we can simulate for the city of Trieste. So I'm coming to the conclusion saying that this real-time testing of precursory seismicity patterns, which is ongoing for more than 2 decades now for CN and about 2 decades for M8, confirms the, let's say, the significance of time-dependent neodeterministic scenarios associated with the forecast by CN and the M8 algorithm. Moreover, the combined use of GPS, geodetic signatures, and seismological information may reduce the space uncertainty of predictions. And in this way, we can provide some time-dependent integrated scenarios for both inland earthquakes, so Azad scenarios and tsunami scenarios that are testable, as we have seen, and provide the basis for warning criteria on some testable basis, and therefore with some confidence level. Most of the results and methods that have been presenting are now published on this recently published book by Elsevier, where studies and applications of a neodeterministic approach are described, including India and Italy, of course, and China and other regions where the method have been applied in different space-time scales. Thank you.
Thank you, ma'am. Ma'am, there are few questions. A question from Sani Usman. How is seismic hazard analysis application in countries that are not prone to earthquake? Please provide example of seismic hazard analysis research that can be carried out in those countries.
So I am not sure I understood properly the question. In an area where you have no information about past earthquakes or seismicity is really moderate or low, well, what you can do is try to figure out, to use past information about past earthquakes to define the potential sources. Maybe you can add some uncertainty, but you need to have some evidences. You can also try to model scenarios for, let's say, faults that are detected, but if you have no evidence for their activity, either seismicity or other indications, it's very hard to, let's say, to assume that you may have an earthquake there. One option is to try and evaluate the potential of possible, let's say, faults in an area by using morphostructural information and other independent observables. So you should investigate the territory. If you don't have historical seismicity nor instrumental one, you may look for other evidences of past events. But I mean, your definition of the sources must be supported by some evidence. If you don't have any evidence, it's very hard to, let's say, to define an hazard. One important advantage of the neo-deterministic is that as soon as you are able to characterize a possible source, you can use it for the modeling of the shaking. You do not need to assess the probability of occurrence. You do not need the recurrence time. So even if you have a short catalog, a short statistic, I mean, you are less in trouble than defining the probability of earthquake occurrence. So recurrence time is not required.
Thank you, ma'am. Another question from Sachin. What is the difference between earthquake forecasting and earthquake prediction?
This is a good question because, I mean, it depends on the language, I would say, because in many languages, we don't have a difference between forecasting and prediction, but there was a huge discussion. If we are saying that prediction is something that is, let's say, exactly saying, modeling or predicting the exact way where the earthquake is going to occur based on a model. So it's like predicting that if I leave, if I, let's say, have a ball in my hand and I leave it to fall down, I know exactly, I can predict the positioning each time. This, we can call it prediction. And forecasting, we can imagine something characterized by higher uncertainties. Some other authors refer forecasting only to probabilistic, let's say, estimates, only to assessment about a possible occurrence of an earthquake that are provided with some probability. But the difference is really, I mean, it's not easy. In many languages, there is no difference between forecasting and prediction, but only one word. So I hope I answer.
Thank you, ma'am. If anyone having any sort of query, please write it in the chat box.
Sorry, meanwhile, some people writing the question. This is also about forecasting and prediction. Some already standard expressions. For example, we say weather forecast. We don't say weather prediction. Yes. Well, if you want to know what weather is tomorrow, you switch on the TV and they say weather forecast. So I think this is also expressions which are people used to apply. I don't think that there is some big difference. You are right. This is mostly a matter of language.
In Italy, we have only prediction, and we speak about weather prediction. So meteo, previsioni, meteo, it's meteo prediction. So we have no translation actually for forecasting, no specific term. So I think that if we really, that's why I'm using it with a slash, one or the other, because if we want to use them in a different way, we need to provide a definition, what is one and what is the other, that should be agreed about everyone, I mean, in the scientific community. There was some discussion.
Also heard that prediction is something scientific and forecast is more or less a judgment about the future. But I don't know if there is really this difference.
Someone says if it is a deterministic model, exact model, it is prediction. Otherwise, it is forecast, if it is uncertain. But if I take a probabilistic assessment with some probability, so some uncertainty, and if I put a threshold, it becomes, I mean, you shift from, let's say, some uncertain to yes or no situation, which is more deterministic. It occurs yes or no. It's, let's say, we are coming back, it's a circular stuff if we don't define it properly. So,
Thank you, ma'am. A question from Bhuvan Kumar. Except geodetic and geophysical tool, any other way to strain accumulation?
so any other way to, let's say, measure the deformation of the ground deformation, or any other observable to detect the preparation of the event? I don't know whether. So, okay, let's take, I assume that the question refers to other observables. So yes, there are other possibilities. There are other phenomena that can be occurring in the, let's say, in the area, in the volume of preparation of an earthquake. Well, they should be physically related to the preparation of the event. We have been testing, for instance, the possibility that radon emission may occur, or radon, or even better, anomalies in the content of uranium in ground waters may change before an earthquake occurs, a major earthquake occurs. But this is reasonable, and it has a model. The main point is to have systematic observations to validate this kind of precursor. And one important point is that this precursor may work in areas where you have the conditions, so groundwaters with significant uranium, which you can measure. This, for instance, was the case of L'Aquila earthquake, where nearby, I mean, 15 kilometers from the epicenter, we have the Gran Sasso laboratory from the National Institute of Nuclear Physics. They were monitoring uranium for different purposes. So that was an opportunity to detect the anomalies. But we do not have such evidences everywhere. And maybe in some areas you don't have the fluids. So it's not widespread. Sorry.
Thank you, ma'am. Now I request Professor J.R. Kyal, sir, to say something on concluding remark. Sir, please.
Okay, thank you. Thank you, Pritha. I hope I'm audible, I hope. Yes.
Yes, sir.
Yes, Professor Peresan, Antonella, you have really educated us this evening. The very comprehensive studies on earthquake forecasting. Of course, there was a little bit, clarification about forecast and prediction. I think all well understood by the audience now. I have some queries, Antonella. That is, you have some success stories, and that is very interesting that you could forecast 2 strong earthquakes or more strong earthquakes in Italy by your comprehensive studies. But I was my query is that along a profile, with the increase of tensile stress, extensional stress, you get higher velocity, and with the compressional stress increase, you get lower velocity. That goes a little bit contradictory to the dilatancy hypothesis, because when there is extensional stress or cracks are developing, then some fluid is expected to enter and the velocity should go down. And in the compressional regime, the velocities may go up. I mean, that is what is my apprehension. But how would you explain this phenomena?
Well, I just can stick to the observations and say that nearby the epicenter of Amatrice earthquake in central Italy, which is a compressional domain, there was a faster deformation. The velocity was higher across the epicenter. So the deformation was more evident. Whereas in the Emilia, in the compressional domain, the situation is different because we do not observe the compression was not affected by the earthquakes, but rather we could see in the along strike, we could see a component of strike slip, not an acceleration, but exactly opposite trend at the two sides of the earthquake.
That is understandable. That is
a
very good observation, and I understand that.
So it's not an acceleration or a slowing down.
In one side, velocity goes up or increases, and the other side of the epicenter area, the velocity goes down. That anomaly is understandable. But in other two profile, with the increase of tensional stress, that was a bit difficult to explain. Anyway, I think everything can happen,
I don't know. Well, it's, I mean, it's not easy to, it's quite similar to also to seismicity, because if I understood properly your question, you mean that if it's moving fast, is accelerating, that I would expect something locked before the event, isn't it? But even with seismicity, sometimes you have quiescence, sometimes you have activation. In the specific case of Amatrice, there were no foreshocks, but there was the deformation nearby the source was increasing. Just around the source, the deformation was faster, but on the other sides, no. So something was going wrong in that specific area, in a radius of about 25 kilometers around. So I think that what is most critical is not is going very fast or is going slow for the forecasting, I mean, for the definition of anomaly, but the contrast. Even in seismicity, when you have change, activation on top of quiescence, or vice versa, quiescence in the middle of an activation, these are bad signals, let's say. So I think that it's somehow similar for the deformation.
Yes,
but there are very detailed models for this area. We can try to investigate.
I hope you have the warning system in Italy, tsunami warning system you have.
Yes.
You are forecasting the tsunami-genic earthquake in the sea floor. That is fine. That is one way of understanding the earthquakes in the sea floor, and then it can generate tsunami. That's okay. But I hope you also have got tsunami warning system, means real-time tsunami, and how far you are from the earthquake source zone, your coastal areas. How far? How long it takes? Half an hour, 1 hour, 2 hours? How much?
We are very lucky because we have a shallow bathymetry from the middle of the Adriatic to the north. The depth of the water is about 50 meters. So it's very shallow. So whenever the earthquakes occur in the southern part of the Adriatic, it takes about 2 hours to reach.
Well, you're very safe. Yeah, that way you're quite safe. And like Indian Eastern coast, yes.
Yeah, it's a very peculiar situation. The point is that the coasts of northern Adriatic are very delicate setting. We have the city of Venice, for instance. We have many lagoons and areas that even with 1 meter tsunami, it could be very critical, can change many things there. So that's why we are spending time to study, because it's very slow event.
Now, I have a very general comment as a common person, well, you are you are doing very good research and understanding earthquake precursors and earthquake, forecasting, and you also with some very good case studies. Very impressive, and I really loved you have educated us with this lecture today. But I have a general comment is that what we'll do if we at all are say precisely can tell that within 10 days there will be a 7 magnitude earthquake or 6.5 magnitude earthquake. Well, as you say, you can organize your disaster mitigation system, but is it the really solution? I suppose I still remember that words of Jim Modi, Professor Jim Modi, in his first lecture in last year. He told that the mega earthquake was not expected; it was beyond their and the mega earthquake did not kill the people. The down shaking did not kill the people. It was tsunami that killed the people. And he also said that their engineers did a good job. There was very minimum casualties by building collapse because the buildings were, earthquake resilient. So I personally believe that earthquake resilient houses are more of practical use.
Yes.
Than forecasting and false alarm, and then even if you do the successful forecasting, how you implement? Can you vacate the whole city, or can you save properties, buildings? So I think the time has come. The governments should take care of the resilient society and house building. Building of houses should be resilient to earthquakes. Of course, we must continue our research to understand the earthquake processes in terms of earthquake precursors and earthquake forecasting. But that is my general comment. And but it was a wonderful. Yes, please.
I really appreciate this comment, and I tried to address these points maybe in one of the slides I was presenting. Maybe I was not very effective on that. So the point is the following. Definitely, the most important thing is to build properly. And for building properly, you need adequate information about the shaking that is possible independently from time. So you need a very good hazard assessment that, like any other information, should be tested against observations, because otherwise you are wrong from the beginning. If you don't have good information about the shaking, you are building in a wrong way. And this is one thing. Then, as I was mentioning, any additional information can be useful. It depends on how you use it. If it is very uncertain, you can use it for very low-key actions. For instance, to increase awareness of the people. If you are expecting an earthquake or a tsunami, you can just send on the TV some, let's say, movies dealing with tsunamis, with earthquakes, how to behave, just without alarming the people, just to increase their attention on this topic. Yeah. If you have more precise information, you can send the people to check, for instance, the stability of some critical structures. There are many things you can do, a really broad range of things you can do to get more prepared. And even if the earthquake does not occur because we have uncertainty, we know that our forecast, any forecast, will have failures and successes. Then whatever you are doing is not hurting, is not creating problems. Evacuation is the worst thing you can do. You need to be absolutely 100% sure that the earthquake is going to occur. For instance, there was a guy crying for alarm before the L'Aquila earthquake. And he was saying, the earthquake is going to occur in Sulmona city, which is 20 kilometers north from L'Aquila. Can you imagine if all the people from Sulmona city was displaced to L'Aquila? Yeah. So this, it's not to be used in this way, but just to take some low-key actions. And I was involved in meetings with where we provided this information, exactly what you have been looking at. in 2012, for the Emilia earthquake, we were providing this information to the Great Risk Commission in Rome 3 weeks before the earthquake. We were saying, look, this area has 40% probability to get an earthquake with magnitude larger than 5.4. And that was an area where such events were not frequent at all. They were not expected. So even a small action to increase preparedness there maybe could have saved some money or something. But do not discard everything. Use what you have in the best way without huge, let's say, actions that are more costly and more damaging than the earthquake sometimes. So we have to learn how to use this information.
Yeah, yes. Thank you, Antonella. It was wonderful interaction and wonderful lecture. You have educated us with real good examples of some success and very comprehensive studies. I think, yes, you will be continuing to teach us on this subject. Thank you so much. Thank you so much. All the best.
Thank you.
Thank you.
Thank you.
Yes. Now over to Pritha.
Thank you, sir. Thank you for chairing the session. Thank you, ma'am, for such a wonderful session. Now, ma'am, we want to convey our small token of love from the students of Techno College of Engineering, Agartala, to our guest, Antonella Peresan.
Wonderful. Wonderful. Yes. It's a really wonderful job he has done. The artist, the student has done.
Now, I would like to request J.R. Kyal sir to grant me the permission for concluding today's session.
Please, please. Thank you so much. You have done a very good job. Thank you. Well done.
Thank you.
Thank you, sir.
Yes.
We will start our 9th technical session tomorrow at 11 a.m. So we will join with the same link by 10:45 a.m. for 9th technical session by Professor Dr. Devajit Hazarika sir and Dr. Santanu Bharwa sir. Stay tuned, stay safe. Thank you all and good night.
At what time tomorrow morning you said? 10:45.
11 a.m. 11 a.m.
As usual.
And the link will be open from 10:45.
Okay. Okay. Thank you. Good night. Good night, ma'am. Seema ma'am. Good night, Antonella. Thank you so much.
Thanks to you for staying so late.
It's a great pleasure. Great pleasure, Antonella. Great pleasure. Thank you so much for accepting our invitation. Thank you so much.
Thanks to you.
Thank you.
See you tomorrow.